In an earlier video, we saw the structure of the convolutional neuron and how many of these neurons in the form of filters are coming together to form a layer, and how the multiple layers are coming again together stacked to implement this binary classification task in this video that we have looked at on cats versus dogs. Now we will be using exactly the same model that we have built for that kind of task, and in this specific case what we were interested now to see is to validate what we have said earlier about some kind of a structure or pattern that we see in the features that the convolutional neural networks kind of learn. So in this notebook borrowed from the book Deep Learning with Python, what we actually can see a couple of things. So first is the so-called the intermediate convolutional network outputs. These are effectively what are each layer kind of presents to the layer above it. And I think it's worthwhile kind of going through that first. And as we said, this is the sort of exactly the same architecture we have seen earlier for that specific data set. And this is the input images, the approximately 150 by 150 pixels, and naturally colored images. And this is the first layer, what it really learns. And as you can see, the output kind of feature map, it kind of presents an almost identical figure to the sort of input input image, except that this image over here emphasizes the edges. So these are as we said, the primitive kind of shapes that the first initial layers of the ConvNet are actually learning. And we can actually go and look at each and every layer. And I think over here, I think this figure over here shows what is really happening. So the initial layers are learning, I will call it a visual content, the same kind of visual content as our eyes kind of see in the image. Let's say you can very clearly see the shape and form of the cat over here. But as you're actually going further, deeper into the network, then the representations that are actually being created are becoming more and more abstract, to the point where this is the fifth layer. As you can see, from that point onwards, we still see some of the feature maps that are being created. Remember, the feature maps that are being created are volumes. So what actually we see here are the flattened version of those volumes. So we plot here the spatial dimensions that are coming at the output on each image, but we are effectively flattening all of the filters that we have used, all of the depth of the feature maps that we have used to create this volume. So here you have the sixth layer, the seventh layer. As you can see here, from the seventh layer onwards, we are not really able to see any of the sort of visual characteristics of a cat. So it's become a fairly abstract kind of representation. Here you can actually also see very clearly the impact of max pooling and how we can actually start with a representation, and what is the max pooling operator with a kernel of 2 by 2 is actually doing, is actually picking at the more essential kind of features that are presented to it. So if you compare this image and this image, so that's effectively at this point we have the representations that are going to be needed after the stochastic gradient descent kind of converges, and provided we don't have any overfitting and so on, these representations are the ones that we are going to be flattening and then feed them into the fully connected layers that constitute our head. And if everything goes okay, this head will actually see and work on those representations to actually do the binary classification. Okay, so This is what we have seen, we can actually see in the feature maps. And I think it's also worthwhile understanding what we actually see now in as far as the filters, what really the filters, the contents of those filters are. To visualize those filters, what we actually do is we define a specific loss function. The details are kind of outside of this course, of the scope of this course, but at a high level, what we do is we try to find input images that maximize the activations that those filters produce. And therefore, in the process of doing so, we are able to, out of this optimization process, to retrieve those filter values. So here we see just the first 64 filters out of the many more that we have used. I think we used all the way up to 256 filters. But here we see the first 64 filters in an 8x8 kind of pattern. And as you can actually see, this filter over here is for the various kind of layers. So these are effectively, we have the layers going from the beginning of this at the beginning of the network all the way to the towards the just before the head of this. So this is the last layer just before the head. And as you can actually see here, in every layer, we learn effectively a collection of these filters that it will decompose the input image. So the input feature maps are being decomposed. So if you go back to what we have discussed earlier about the operation of the convolutional kind of neuron, so imagine that you have now not only just one filter, but you have, let's say, 64 of them. So each one of those filters is one component out of the, let's say, 64 that the input feature map will be decomposed. So you can read about this as those are the components of that decomposition. So this, so in the last kind of layer over here, we have 64 components. For those who have some background on principal component analysis, there is something to it along those lines. But the composition over here is definitely exactly the same as any other decomposition. It's just that these components, as the layers are becoming deeper and deeper, these components are look quite different. And this, as you can see here, the filters are simpler in the first layers and becoming more and more complicated in the subsequent kind of layers to match the sort of non-visual, intuitively visual complexities that we have seen in the output activation maps or feature maps that we have seen earlier.